Hello students, I hope all of you are doing well with your family members and everyone is fine during this tough time. I thought that I will continue to teach you the course through YouTube videos, and in last week I have uploaded two videos and I hope that you have gone through it along with the soft copy of the book and that particular chapter that we are going through. Now this lecture is in continuation with the previous one where we have learned that how to formulate the expression for the currents. Now as you know that the reference current last time that we have found out that we have formulated with the help of the PQ theory or instantaneous reactive power theory. Okay, and in that we have learned that by substituting the right amount of powers, the desired amount of powers from the compensator, it is possible to extract the reference currents. Okay, so you can see it here. Actually these are the compensator powers like PF0, and this is PF alpha beta, and this is QF alpha beta. Alright, so that makes the reference powers, and we have substituted these values to find out the reference currents which are shown here. These currents are in alpha beta 0 frame. Obviously, we will convert these currents into ABC frame of reference where we can find out these quantities in ABC reference axis, and once we know in ABC, then we can realize them through a power electronic circuit. That point I have explained in the beginning, and again this for the sake of completeness I am adding it once more, that these currents are here. So if you look at this diagram, this is the actual circuit. Okay, this is the actual compensator. Where we have realized this compensator with the help of a voltage source inverter. This whole circuit from DC link capacitor voltage to power electronic switches and to the interface inductors is called the voltage source inverter. So as you can see, this is one of the topology which is used to track the reference current which we have found with the help of some formulations. Fine. Alright, so this is one of the topology, and there are many such topologies. Okay, but I am not going into these details. I think you can refer the references of this chapter. Okay, but however, we are only talking about the most generic voltage source topology called a neutral clamped voltage source inverter topology. This has two DC capacitors forming a DC link. The midpoint of this DC link capacitor goes to the neutrals of the system neutral as well as the load neutral. And obviously for the perfect compensation, all this neutral current which is here, okay, I0, this must be directed to this path here so that no amount of current is being left, as that is ISN must be equal to 0. Okay, now once it is clear, then we can think of the switches as a on-off device permitting a certain voltage across the point ABC. And it is not very difficult to perceive that what will be the nature of voltage at point A, B and C. It will be the train of pulses of plus minus VDC1 and minus VDC2 respectively. Since VDC1 and VDC2 are approximately same, therefore we can say plus minus VDC. So we can say that VDC1 and VDC2 here is approximately the same. So this is approximately equal to VDC2 equal to VDC, and hence the voltage that we apply at the point A, B and C are plus minus VDC depending upon which switch is closed and which switch is open. The total DC link voltage, if you see, is actually VDC. Okay, and VDC is VDC1 plus VDC2. This is the total DC link voltage, and the DC link voltage has to be maintained constant. I will describe this in the coming point. At the same time, the individual voltage across these capacitors must be maintained a certain value, so that when you realize the currents with the help of switching, okay, they must be able to track the given reference current. Now this is the standard inverter topology. You can see this is S1, S3 and S5, S4, S6 and S2. Similarly, we have a diode D1, D3 and D5. This is D4, D6 and D2 respectively for the legs A, B and C. Here you have a inductance. That inductance is called interface inductance, which connects the midpoint of these legs to the point of common coupling. So this is called the point of common coupling. If you look at here, so this is basically point of common coupling where the compensator and the load and the source are connected together. Okay, so I'll just write here the terms so that you remember them, that this is called PCC as point of common coupling. Also, in the previous lecture, I have explained that how these currents are realized. The actual currents IFA, IFB, IFC star. So if I say IFA and IFB and IFC, okay, they must follow their reference currents IFA star, IFB star and IFC star. Okay, so IFA must be following IFA star and IFB following IFB star, IFC is following IFC star. Why? A way of switching. And one of the scheme that is used to switch this inverter is called hysteresis band current control. Hysteresis band current control, in which we make the hysteresis band around the reference current of plus minus H. Alright, for example, if you have a current here, this is I, FA star, so we make the band plus minus H, and these upper and lower limits of the reference currents was IFS star plus H and IFS star minus H. These are being compared with the actual current. If you remember, I have done this earlier. Maybe I can go through this logic before I go further. Okay. Logic is here. Now as you can see, this is called hysteresis, current control. Okay, now in this, what we are doing, we are comparing the actual current, which is IFA, against the IFA star plus H, this term, okay, this term here, and then IFA star minus H, and we take decision whether the switch, upper or bottom switch, should be on or off. Now as you know that these two switches in the same leg, they are connected to the DC link terminals through DC storage capacitors. So obviously the two switches cannot be on at the same time. Rather, when there is a transition of switching, the one has to be turned off first, then after delay of 2 to 3 microseconds, the other switch will be turned on. This mechanism is called a blanking time circuit, or it is deadband time between the two switches. This ensures that the inverter operation, do not short circuit the DC link voltage or DC link of the inverter. So as you can see, when IFA is greater than IFA star plus H, then the top switch is off and the bottom switch is on. So remember here that I have used SA. Okay, we have used here SA. So basically, when you say SA represents the status of the top switch, and SA bar represents the status of bottom switch. Similarly, SB and SB bar, and SC and SC bar. Okay, so these status of the switches are generated using the switching logic in these lines. So when we are having more current than the upper limit of the reference, then I have to make the top switch off and the bottom switch on. So when S is equal to 0, basically it implies the top switch is off. And when it is 1, it implies the top switch is on. And vice versa for the bottom switch. So you can see when S is equal to 0, SA bar is 1. Similarly, when IFA is less than IFA star minus H, the SA is 1 and SA bar is 0. And in between there is no operation, and this switching logic continues at the quite high speed, maybe a bandwidth of the 10 kHz, 20 kHz, depending upon the processor speed and the speed of the inverter, the capacity of the inverter, di by dt of the inverter. Normally, it goes 20 kHz to 50 kHz, okay, for the rating of the current from 10 amps to, let's say, 50 amps. In the reverse order, okay, higher the current, the less will be the switching frequency. Less the current, you can operate at higher switching frequency. Understood? This point is very important, that how the inverter is used to realize the reference currents and what is the mechanism of generating the actual currents from the reference currents. These schemes can be implemented online or on a real-time basis using any DSP processor which has a real-time interface. In actual systems, we sense these load currents. If you see the algorithm, then we compute powers, if you remember, okay? And from powers, we use the currents, reference currents, and from reference currents, we find out the actual currents in the ABC frame, here, ABC, and finally, we find out the values of these currents, and they are being monitored, the actual currents are being monitored against the upper and the lower limit of these currents. Fine. Many times you need to find out the performance of the compensator on simulation basis. You need to simulate the performance before you go for experiment. You can do it by a number of methods. You can write your own program, or you can write the MATLAB Simulink, a block diagram simulation program, or you can use any other software to implement this. But writing a simple code for this system and simulating it will give you a very direct experience for simulating any physical systems comprised of the inverter or any other power electronic circuit. This is often done with the use of the state space modeling of the inverter. So therefore, you can have the state space modeling of this inverter, and you update those states as a function of time, as a function of the samples of time, and these series of time samples make it the variables like voltage and currents at different points, and you can plot and you can see the performance of the whole system. So in this line, in the coming few minutes, I will talk about the state space modeling of the voltage source inverter. You can extend this idea to any other power electronic based systems or any other compensator. It could be a voltage compensator, it could be a voltage and current UPQC, it could be a DVR, it could be a D-Statecom, it could be a static transfer switch, anything. The concept remains same, and you can implement, you can write the coding in any simple software like C++ or MATLAB script code to understand the behavior of this kind of systems. So now I will go for the state space modeling. Before I go for this, it is important to understand that in this particular configuration, we have 3 legs, and each leg is independent. Okay, here if you see, each leg is independent through the neutral. If you see this leg, then you have this leg and this leg. All these 3 phases are independent through the neutral, because neutral is a well-connected point between the load neutral here and the source neutral and the load neutral and this compensator neutral. Therefore, we can take any one phase and try to understand that how the space modeling is there for one phase, and we can extend this idea to other 2 phases, And then we also have to write the state space equations for BDC1, this CDC1 and CDC2. Looking at this diagram, we can say the order of the system will be 5:5 because the number of state variables here are 5. C1, C2, L1, L2, L3. There are 3 inductors and there are 2 capacitors. So these form 5 state of variables or 5 state variables, which means the system order will be 5/5. Please note the direction of currents that we have taken. We have taken the current IFA is going up, and here the current I1 is here. Very important to note, this is I1 here and this is I2 here. Okay, so direction of I1 is this and the direction of I2 is this. The direction of IFA and IFB and IFC are this. Okay, so with this we can write the first order differential equations for the circuit which starts from, let us say, A, goes like this, comes back here and goes here and goes here and make a complete path to this capacitance. This part does not play active role because the load impedances are quite high as compared to the source impedance. Hence current will nearly follow or almost follow this path, the source side path, okay, this path. And ILA depends upon this voltage. So while modeling, we consider the source part rather than the load part. This is very important to understand because the equations which govern the voltage and current laws, Kirchhoff voltage law and Kirchhoff current law, will be applied to this path due to the least impedance path for the currents. Now, knowing this, we'll go further. So we are here at the section 5.2.1. Please refer the soft copy of this chapter which I have sent by attachment to you by mail just now, and you combine the soft notes and what I am saying through this lecture. So as I said that since it is a 3-phase 4-wire topology and each phase is independent through the neutral, I have shown only one phase, and that is enough to understand the behavior of the circuit or the behavior of the compensator. Let us say that due to the hysteresis current control action, the top switch is closed and the bottom switch is off. You also remember when I say top switch, okay, this is the top switch here. This is the top switch. Top switch is comprised of S1 and D1. And the bottom switch is comprised of S4 and D4. So when I say the top switch is on, basically means you are turning the switch S1 on, but the direction of current is opposite, D1 play the role. So S1, D1 together make the path conducting. Similarly, S4, D4 together makes the path conducting. So when S1 is on, the path for the current is shown here. Okay, you can see here the path of current is like this from here to, it goes to this way and this way and this way and this way. Okay, and it comes down back here, then goes back here and comes here and finally it goes through this path. So basically this is point A. So A point is applied a positive voltage. Okay, the voltage is basically between point A and point N. We are applying a voltage VDC1, positive VDC1, which is same as VDC. Obviously, since we are applying a positive voltage, the current will increase, and hence the current will rise. Current keeps on rising till we check again whether the current is more than IF star plus H. If the answer is yes, then I will make the bottom switch closed and top switch open. And for that condition, this is the circuit. This circuit, the bottom switch is now closed and the top switch is open. And if you see this path for the circuit, if you see, then you can see the current. Since I have taken this direction of current, so path is from here to here, back to here, and this goes to this point and comes back here and comes back to this closed path like this. Now this time if you see the A point, the leg point here is connected to minus BDC2 because the negative point is here. Okay, the negative point is here. The negative point is here. So minus BDC2 comes here. So across point A and N, basically we are applying minus BDC2. We are applying minus BDC2. It's like this basically. In the first case, we have a RL circuit like this. And we are applying a BDC plus across the back EMF also, plus and minus. You can say this is plus and minus. This is plus, this is minus, this circuit. In second case, we have this circuit. This is minus VDC2 and this is L. This is same plus and minus, and we have this. This is minus VDC2. This is VDC1. Okay, this is AC source. In this context, it can be called as the back EMF. The current direction is IFA. This is also IFA. Now you may say that, well, if the negative point is connected here, okay, that means this point is positive. How the switch can conduct? Well, I have made the switch on, but switch may not conduct. D4 may conduct because the current in the reverse direction. Therefore, in this particular case, rather than S4, the D4 will conduct. So, the switch comprised of the D4 and S4. Okay, so it provides a conducting path for any direction of the current. If it is plus, the D4 conducts. If it is minus, the S4 conducts. Clear? So now you have understood that depending upon the current status, we make switching on and off for, let us say, leg A phase. And for that condition, we have seen that if what happens if the top switch is on and the bottom switch is off, or when the top switch is off and the bottom switch is on. Now for these two conditions, We write the first order differential equations to describe the behavior of the system. So you can write the Kirchhoff voltage law from this circuit. Okay, this circuit. So if you write the Kirchhoff voltage law, you can say drop across the inductance and resistance, and then back EMF plus here minus BD7 equal to 0. This forms the first order differential equation dIFA by dt equal to minus RF by LF IFA minus BSA by LF and plus BDC1 by LF. Now LF is same for all phases, so RF is the resistance of the interface inductance LF. So generally we express the pair like LF and RF. Okay. RF ideally must be equal to 0, but since any inductance has some resistance and therefore small resistance may be present in the inductance itself. Now let us say the S1 is open and S4 is closed. Then you can see from this diagram, the second diagram here, okay, this diagram, that except BDC1, it becomes minus BDC2. Other parameter remains same. So driving force is now minus BDC2. So wherever you see BDC1, it becomes BDC2. You can see it here in this block. If you see, this is minus BDC1, BDC2 by LF. This is plus BDC1 by LF. Okay. That's only change. The driving force is plus BDC in case of the S1 is on, and driving force is minus BDC2 when S1 is off. And the S4 assumes the complementary position. Clear? Now how these two currents can be combined? Through a switching action. These two equations. If I use switching function, how it is possible to express these two set of state variables, state conditions in form of single equations? Obviously, I will add the switching notation for the top and bottom switch. And the previous discussion I said that the top switch refers SA, the bottom is SA bar. Clear? So if I use this SA and SA bar notation in these equations, we can write a single equation. Okay, that is the dIFA by dt equal to minus RF by LF into IFA plus SA BDC1 by LF minus SA bar BDC2 by LF minus BSA by LF. Okay. Now see it here that if SA bar is 1, then we apply BDC1, hence the equation becomes BDC1 by LF. When SA bar is 1 and this is 0, then we apply minus BDC2. So this equation expresses both the conditions together in form of the switching status SA and SA bar, these two conditions. This idea can be extended for other two phases, that is phase B. This is for phase B and for phase C. Same way, except that I have a switching function SB, SP bar, here it is SC and here is SC bar. The voltage B, SA becomes BSB here and this becomes BSC here. The current is IFB and IFC. Okay, so similar to this, we have identical equations for phase B and phase C. So there are three state equations. but there are 5 state variables. Which are those 5 state variables? 3 inductor currents and 2 DC capacitor voltages. 3 inductor currents and 2 DC storage capacitors voltages. So we need 2 more equations to make a state space model. Okay, so for that we have to look what is the equation for the voltage across the DC link, each DC link capacitor. Okay, so for this we will look the same diagram which I have shared in the beginning, the inverter circuit. You know the current I1 and I2. I1 current was going away from the DC link capacitor VDC1 and I2 was also leaving the VDC2. So obviously the I1 must be sum of the current IFA, IFB, IFC through a switching function. For example, if the top switches are on, then it must be sum of IFA plus IFB plus IFC. If the bottom switches are on, it must be IC bar IFA, SP bar IC, SP bar ISC. If the SB is 0, then of course IFE will not contribute anything to I1. So we can directly write the expressions for I1, I2 and I3 in terms of the components IFA, IFB, IFC and its switching functions. Okay. See, since top switches form the status SA, SB, SC, therefore I1 equal to ISA into IFA plus SB into IFB plus SC into IFC. The first equation here, this one. And the second one is I2 equal to SA bar IFA plus SB bar IFB plus SC bar IFC. Now you see the nature of these currents. If you look the previous diagram which I explained like this, you have a BDC1 here, this is BDC2 here, and this current is this point NS, and this current is I1, this is I2. This is BDC2 here, and this is BDC1 here. Okay, between this point voltage. Now I know that the relationship between the DC link voltage and the current through the capacitor, the DC link capacitor. Okay, here the current is outgoing, this is minus, this is plus, and therefore the relationship between the capacitor voltage and current is this: CDC1 dBdC1 by dt equal to minus I1, because current is going away from the plate. So when you have this kind of notation, okay, this is plus and this is minus, and current is flowing in this direction, call it IC, and the voltage is BC here, this is plus, this is minus, then the relationship is C dVC by dt equal to I1. Now hence current is opposite direction, therefore the current is equal to minus I1. Okay. Similarly, for the other one, the direction is opposite. This is I2. This is I2, plus to minus, and therefore it is positive I2. So therefore we can write CDC2 into BDC2 by dt equal to I2. Okay, so these two set of equations. Now from that we will get the first order derivative of the DC link capacitor voltages in terms of the current and current in terms of these filter currents. So expressing I1, I2 from these equations and putting it back here, we will get these equations. So dVdc 1 by dt equal to minus SA by CDC into I of A minus SB by CDC into I of B and minus SC by CDC into I of C. Similarly, substitute I2 here, we will get SA bar by CDC into I of A plus SB bar by CDC into I of B and SC bar by CDC into I of C. So these are another two states. So how many states total? There are 5 states. 3 inductor currents and 2 DC capacitor voltages. Three inductor currents and 2 DC capacitor voltages. Putting in the matrix form, we can write the equations here. This is dy dt term. That is x dot is equal to ax plus bu. So here, what is x? IFA, IFB, IFC, BDC1, BDC2 and dy gt of this equal to, this is A matrix. And here are these x variables, IFA, IB, IFC, BDC1, BDC2 and this is the B matrix, okay, in the form of this equation. Now x represents here a state vector, A is the system matrix, B is the input matrix, U is the input vector. In one sense, U is not input vector, it is just there because there are back EMF corresponding to each phase and they are not controlling voltages, they are present with the property of the system of the configurations. And we have to nullify their effect by raising the BDC1, BDC2 for well above the value of the peak of system voltage. We will see in that. Okay. How to solve this system with this state variable using MATLAB or using the C++. Okay, I will describe that part in the next class. Maybe tomorrow I will upload the next portion, and meanwhile you go through this section and yourself you go through the whatever I have discussed in the class. Also please solve the questions in the back of this chapter, which is given along, the questions are being given along with the answers so that you can verify your answers as well. Alright, so I will stop here and we will meet tomorrow or maybe day after tomorrow. When I prepare this lecture, I will upload through the YouTube channel. Thank you very much.